All right, good afternoon, everybody. Welcome back to another live stream. Today is going to be a little bit of a fun one for me. Fun in the sense that, so I've been blogging for about 10 years now. I originally started blogging, doing like pure business posts and like philosophy posts. And then when I first started to get into blogging about AI ML, one of the very first things that I had written a series of posts about was MLflow. That was in 2020, which is completely just strange to think that that's been 6 years ago now. We're now kind of coming full circle where I honestly have not had a particular use for MLflow myself until recently again. So it's kind of cool to now come back here in 2026 to re-review MLflow. And then also, of course, a lot of changes have been made along the way with MLflow. The biggest change, namely, is the fact that they've added a bunch of stuff to support generative AI. And so today's stream is entitled MLflow for traditional ML. And that is because we're going to focus on the traditional ML stuff today. And then in the next stream, there may be two streams, I haven't decided that quite yet, we will cover the generative AI aspects of MLflow. And the reason for that we're starting this way is, again, because MLflow started for traditional ML, and then it's since added these things for generative AI. I think it's good to have that basis for how to think about MLflow from that traditional ML perspective. So what is MLflow? So MLflow is an open source tool or open source platform. You can look at it either way. Open source is still the key here. Okay, I'm going to admit something kind of stupid, like ignorant about myself here. When I first did my exploration of MLflow back in 2020, I did not realize that Databricks had created MLflow. So the company Databricks has created MLflow, and Databricks has baked in MLflow across their entire platform. Now, this stream is not going to necessarily cover Databricks per se. I am learning Databricks right now, and I do see that a lot of these concepts that we're going to be covering today, and then with the generative AI stream on MLflow, do have translations over into Databricks, but it's not a one-for-one translation necessarily. So we're going to specifically stick with the open source version for this stream and then for the generative AI stream. So let's go ahead and jump into things. Now, I want to first talk about the architecture of MLflow. And by architecture, I mean, how does this thing actually manifest? What's going on the back end, etc. And the best way to do that is going to be by sharing my screen and then just showing a diagram here. So by the way, two things. Number one, what I'm displaying on my screen here is my GitHub tutorial of like this whole thing here. So you can find this out on my GitHub. Now, because I have not completed the content for the generative AI stuff, I do have this note in here that says everything's still currently a work in progress. So just expect that things may change here over the next month or so as I work out that new content. But like I was saying, so I want to jump down here to this picture. This picture actually comes directly from MLflow's website. I did not create this myself. What they were basically intending to want to do here is showing three different ways that MLflow can manifest. And I'm actually going to hone in on this right side, and then we'll jump back to the left side, because the left side, number one, is actually what we're going to do here. But I think the right side of the picture actually covers a more robust production version better than the other two sides do. So essentially, you can see here at the top, we have our where we might be doing our work. So you can see there's a local host. This might be your local laptop. It could be your desktop or a server that you normally do your data science work in. And then so MLflow has these what they call the tracking APIs. And the tracking APIs, given that most of us in the ML space work in Python, this largely manifests as the MLflow open source Python library. And so this is our way of actually writing the code and such that interacts with MLflow on the backend. So let's talk a little bit about this backend here. So you can see here with the backend that we have kind of three components going on here. And it's kind of confusing to me why they labeled them as such, because they don't necessarily refer to them this way. Here, let me actually go to MLflow's true website here, you can actually see they actually refer to them kind of by different names with backend store, artifact store. So I'm going to stick to this nomenclature here, but I'll do what I can here to kind of highlight what the correlation is here. So you have, first of all, we have this thing called the tracking server. And so the tracking server is kind of like the beating heart of MLflow here, where when we are writing our machine learning code or we want to do model serving, we'll get to that. Well, I kind of just spoiled it a little bit. One of the offerings of MLflow is that you can actually serve models directly from MLflow, and we'll demonstrate how that works all with real code later on in the stream. But essentially, so this represents like the how a user interacts with the MLflow, not just from this perspective of interacting with it from the API, but it also does have its own user interface where we can actually go in and look at things of all the different ways in which we can interact with MLflow. For traditional ML, I'm getting ahead of myself a little bit, so let me pump the brakes on that first. But let's talk about these other two pieces here, what they're referring to as cloud storage in the database here. So cloud storage, as they refer to it on this picture here, is actually, again, so note that they don't actually, they're not using their own terminology consistently here. But so that would be this artifact store here. So the artifact store it's a block-based storage. And when I mean block-based storage, I mean something like AWS S3. And I actually think that this might be slightly indicative of a bucket here, if you will. So anytime we train a model and we need to store some larger files, such as the serialized trained model, whether that be a pickle file or a .pth file or something like that, then it goes into the cloud storage. I'm sorry, the artifact store, because it doesn't necessarily have to be cloud storage. It can be if you have your own, if MLflow you can install anywhere that you have like the proper block storage availability, a database storage availability. So it can be its own server, and then this could be simply like a file path system. And we'll jump back to that whenever we talk about how we're actually going to leverage MLflow for our own code here today. But yeah, so anyway, with the artifact store here, that is essentially what that's doing, is holding our artifacts and such. And then associated directly with that is a database backend. And the database backend is going to contain things like metadata about like the various models that we've registered, or different metrics that we've captured along the way, etc. So basically storing a bunch of structured data that directly correlates with the artifacts and the artifact storage, all being manifest through this tracking server here. So that, if this is a little bit confusing right now, I hope that it'll make sense as we get into the stream, and then we'll actually be able to see directly for ourselves with our own work how this is actually kind of working out. All right, so that is like the production version of MLflow. So let's talk a little bit about how we are going to be doing our own interaction today. So we're actually going to be making use of this first column here. And so this first column here, you can see that it's largely the same. It's just that whenever we're going to run our stuff, we're just going to run our stuff locally on our own personal laptop, our own personal desktop, and then it's just going to save everything to just the local file system. And I don't know how wild I am about this picture, because I actually think this middle picture might be a little bit more representative. I do understand why they separated it out, though. The reason they separated it out is because they are actually kind of indicating that you might, with this second pattern here, actually stand up something like a tiny SQLite database, a tiny Postgres database. And so when we're actually using this first pattern here, when we start up MLflow for the first time, what's going to happen is it's going to create this, I think it's called MLflow.db, which is basically like a database file, but we're not actually creating a legitimate database, if that makes any sense. So so let's actually just go ahead and jump right into things. Now, I did recall right now that I didn't delete these things, so let me delete those really quick. Okay, so what I am going to do, this is, by the way, the finished notebook that we're going to be basically replicating this entire notebook here, but let's get out of here for a second. Collapse my countdown thing there. Okay, so what I'm going to do is I'm going to go into here, into my terminal. Let me make that a little bit bigger for y'all. I'm going to go into my repos, get into my MLflow tutorial repo, and throughout this entire repo, I'm probably just going to be making use of Jupyter Notebooks the whole time. At least for today's stream, Jupyter Notebooks suffice for everything. I can't say quite yet for the generative AI stuff, so there may not, because what I typically do with my other projects is I will kind of demonstrate what I can as part of a Jupyter Notebook, but then move it into like the source or SRC directory with hardened files. And I don't know that that's particularly necessary for working with MLflow, as you'll see here in a little bit. But anyway, so let me activate my virtual environment. And I actually have now done this little thing where I actually have like my own custom little command that actually turns on my virtual environment for me. So I'm using UV, of course, and then so if you're using UV, it's as simple as, I mean, I'm going to do it right now, but it's not going to do anything. So I'm going to do UV add MLflow, and then you'll see that it installs everything. It looks like it went ahead and updated some things. Oh, it looks like Starlet's up to 1.0. Interesting. All right, I'm going to clear that out. All right, so to start with MLflow, it is as simple as running the MLflow server command. All right, so let's go ahead and run that. And what this is going to do is it's actually going to create those files behind the scenes. In fact, like the artifact store file and the backend database store file behind the scenes. And then it's also going to start up the user interface. And I just want to show that really quick here in this secondary the secondary tab here. So if I go into notebooks, so this is where I have instantiated my MLflow server from. So then if I do ls-a here, in addition to, well, so it's not showing the directory itself yet because probably nothing is in there, but you can see that we now have this mlflow.db, and that is the database file that is representing the backend store. And then later on, once we actually start populating things to the artifact store, then you'll actually see a new directory pop up in here that's called, entitled MLruns. In fact, let me see if I can cd into that MLruns. I don't think I can just because there's nothing in there yet. Yeah, but let's go ahead and look at the user interface. So you can see here that by default, the user interface starts at the local host of 5000. So I'm going to pop into my browser here. Let's go ahead and go on over to there. Okay, so this is the MLflow user interface. Now, I'm going to not necessarily focus too much. Like I started at the outside of the stream, we're not going to talk about Databricks too much. However, I do want to mention one thing here. This is the biggest deviation between the open source MLflow and the Databricks MLflow is probably this UI right here. And it's not even that big of a deal because it's just a simple UI that's just manifesting things back to us. It's just that the reason that you don't see this user interface on Databricks is, again, Databricks created MLflow, so they just took all the functionality of MLflow and baked it directly into Databricks to make a seamless experience on Databricks. That way you don't have like a Databricks UI and an MLflow UI. It's just the Databricks UI, and then MLflow is just kind of powering things behind the scenes. So as far as I've seen, that's the only real major deviation between the open source version of MLflow and the Databricks version of MLflow. But anyway, so when you actually start this up for the first time, it actually creates a default experiment that you can see here. And we'll cover some of these terms here in a little bit. But I just want to kind of show here, it doesn't look like anything's been actually shared into here yet. And that's okay. We will be able to kind of see how things shake out as we continue along with our stream here. But this is where I do want to start covering some concepts. And so something that you will start to see, especially as we get into the generative AI space, is, again, recall that MLflow started with traditional ML and has since grown and grown and grown. So they started with terminology that I think made sense at the outset, but now that terminology has kind of a little bit outgrown what the actual concept it's trying to serve here is. So the reason I say that specifically here is when basically everything rolls up in MLflow to an experiment. And that made sense in traditional ML when you think about like hyperparameter tuning, where with hyperparameter tuning, we're obviously doing a bunch of combinations of these different parameters and seeing which combination of hyperparameters is going to produce the best inferences for a model. And so then whenever we did, let's say we did 30 different trials of different hyperparameter combinations, the cool thing that you'll see here, and we'll come back to this UI as we continue along in the stream, is that you will be able to see all of the different trials that we did here and see all of the different validation metrics associated to each of those respective trials in this nice clean UI right here. And so that's another concept I want to touch on here is every time we run an execution of code, it's a specific execution of code. I know I'm struggling a little bit today because generally speaking, the way that I like to structure these streams is we start with an introduction, we introduce the concepts, and then we show the code. I am now quickly beginning to realize that trying to share the concepts is kind of confusing if you don't see like the code itself. In fact, you know what I'm going to do is I'm actually just going to run this whole notebook really quick here, and then I'm going to delete everything just to have things populate up in here. So this, again, we'll come back to this notebook, but just to be able to show things. So now you can see as this has been running that we have this new experiment in here called local demo. And so within local demo here, then you can see this is what I was talking about. So most data scientists these days are using Optuna to help with hyperparameter tuning. And you can see that we got a little toggle next to here. This is exactly what I was talking about. So see that we have the 30 different trials here. So if I wanted to look at one of these trials, let's see how it did. Let's just look at Optuna trial number 14, just as an example. You can see that we have logged the respective validation metrics associated to this train, and then all the different parameters associated to it. And then you can even see some additional metadata off here on the right and such. So this is what we would, again, refer to as a run. So in this particular case, the run represents the Optuna trial. But a run is not necessarily limited to the Optuna trial. It could be the model training instance. It could be several other things. But all runs roll up to an experiment. So an experiment is basically just like a logical container to hold these runs. And so there's a one-to-many relationship associated with experiments and runs. So you have one experiment, and you could have many runs underneath that experiment. Okay. So that is, I think, is that all I want to cover in the UI today? Again, so you can see that there's actually this GenAI tab here. We're not going to touch on this at all today because we're going to cover that in probably a future stream. And then eventually, actually, let me cover this right now here. So we have the model registry here as well. And so again, I had already, these were just produced by that notebook that I just ran. And again, we'll recode everything. In fact, I'm going to I'm going to shut this down. I'm going to delete this whole backend just so we can have a fresh copy of MLflow that we're working with. But you can see that with this model here, that when we go into it, it's actually, sometimes this local UI can be a little bit wonky, like it doesn't want to load properly. Where is the thing that I want to show here? Iris model, registered models, version 1. I always get a little bit confused from the UI perspective of where I need to be clicking on things. Maybe this source run, is this it? Okay, I'm a little bit lost here. Okay, so I think this is the view that I wanted to see. So you can see I was trying to look for this iris model. So if I click on this model here, then you can see all of the different metrics associated to it, the parameters. And then you can see there should be nothing for traces because I'm not doing anything with traces here. Now, again, it is actually kind of good timing that I did the OTel stream or the open telemetry streams right before this, because that is exactly what we're kind of seeing here, is if we wanted to capture the traces from our traditional machine learning model, we can. This is going to become a lot more important whenever we cover the generative AI side of things. So I'm not going to touch on this piece today, but then you can also see the various artifacts associated with the trained model. And again, we will come back to this here. Okay, so I hope that kind of gives you a general sense of the MLflow UI. So I'm going to go ahead and shut this down. I'm going to delete those backend files, and then we'll go ahead and get going with the code. Is that all I wanted to cover there? in terms of concepts, yes, I think I'm good for the concepts now. So, well, at least now we can see that, yes. So the artifact store, like I was saying before, because we are not connecting to something like AWS S3 as our artifact store, it's just saving things to this local directory. And so if we actually change into that local directory, then we got to change again into that one. Then you can see that I think that all these hash things here are the various runs that were applied. And of course, the reason that there's so many is because we did a trial of the 30 a round of the 30 trials for hyperparameter tuning using Optuna there. So there should be something like 31 or 32 in here because it also trained models twice as well. Okay, so I'm going to go ahead and CD out of that. What is going on there? I don't know what's going on there. All right, so I'm going to go ahead and open this and then delete those extra things on the back end because we don't want those for now. Okay, let's actually go ahead and hop into some code. All right, so I'm going to go ahead and first of all, I'm going to make that a little bit bigger. I'm going to switch to a different view on my screen, and then we're going to start fresh from a fresh notebook. So I'm going to close these out, and I'm going to create a new file here. I'm going to call it tradml, because I'm lazy, _stream.ipynb. And so the very first thing that we're going to do here is we're going to demonstrate how to do hyperparameter tuning and some cool things that MLflow offers to support hyperparameter tuning. So we are largely going to be making use of just scikit-learn today. So you may need to do an install of scikit-learn. Now, again, keep in mind that I am using UV here. So if you want to look specifically at the dependencies that I am using, simply just go to this PyProject toml file. And if you do a git clone of this, if you just and you had UV installed, you could just do UV sync and then you'd be good to go here. So let me go ahead and go back to our notebook. Let me go ahead and select my virtual environment as my kernel, and we're ready to write some code. Now, very first thing we need to do is we need to write a bunch of imports. And I'm not going to necessarily touch on these imports per se. We'll talk about what they mean further on down. So we're of course going to import OS and sys since we use those quite commonly across all of our projects. We're naturally going to import MLflow. We're going to import Optuna for hyperparameter tuning. We're going to import both NumPy and Pandas for some machine learning stuff. NumPy as MP. Import Pandas as PD. Then I'm going to demonstrate something, but I don't know how much I actually will recommend what I'm going to demonstrate here with this particular library. But this is not super important, but we'll demonstrate it anyway. And then we have from MLflow.models import infer signature. We'll talk about what this is and what a model signature is when we get to it. And then finally, we're going to have to import a bunch of scikit-learn packages. And in fact, I'm just going to lazily copy and paste everything that we're going to be looking at. So across this notebook, we are actually going to be working with two different data sets to train two different models, and I'll share why later on in the stream. But first, we're going to start off with the iris data set. So the iris data set, this is a classification data set that is looking at different iris flowers, and the features associated to it can help produce trying to determine what is the appropriate class of the flower. I believe that's what it is. We're not doing anything fancy with this data set. In fact, we're not doing any sort of feature engineering with the data set or anything. We're basically going to load it in, split it between a train and a validation set, and then be on our way. Not going to concern ourselves too much with the actual build of the model itself today. And then the other data set that we're going to be using is the wine data set. And I guess if I'm being honest, I really don't remember anything about the wine data set. And again, it kind of doesn't matter for today's purposes. We're just trying to demonstrate how MLflow expects things. So then we're just importing a couple of other things standard to the scikit-learn, importing random forest classifier, logistic regression as our model algorithms, train test split to do that train and validation split, standard scaler to produce to scale the data appropriately before we feed it into the logistic regression model, using the pipeline to help kind of manage that facilitation between the standardization and the model train, and then of course importing all of our validation metrics. So there's all of our imports. Now we need to do a little bit of configuration with MLflow. And so one of the things before I start typing any code here that I want to talk about is recall, well, I went ahead and blew it all away, of course, but recall back in the UI where we were capturing like those metrics and the parameters and things like that. There's two ways that you can capture those. Number one is you can do it a little bit more manually, and we'll demonstrate both ways. So the manual way is simply where you explicitly define, here's the things I want to capture, whether here's the metrics I want to capture, here's the model I want to log, etc. Whereas the other way to do it, and the way that I kind of like to do it better, assuming that everything's just kind of plain vanilla, is this concept called auto logging. And what auto logging is so MLflow supports a number of different machine learning frameworks. So it supports scikit-learn, it supports XGBoost, PyTorch, etc. And so as long as your model framework is supported, then you don't necessarily have to do the manual stuff itself. It will automatically determine that for you and automatically log those parameters, those metrics, etc. So that's kind of nice that it does that for us. So let's go ahead and start to configure things. Now remember, we are going to be running a number when it comes to executing our code, we are going to be creating a number of different MLflow runs, and then we have all those runs that roll up into one experiment. So naturally, the very first thing that we need to do is we need to set our experiment. So we're going to say set experiment, and we're going to call it local demo. You can call it whatever you want. I'm just calling mine local demo. And then the next thing, like we were just talking about with auto logging, we're going to turn on auto logging. So we're going to say mlflow.sklearn .autolog. Now, there's different things that you can actually configure with auto logging. So I'm going to actually do two different options that are not default. The first one is log models equals false. Log models equals false. And the reason that I am purposefully making this false here is whenever we actually do each run through Optuna, it is producing a model artifact, it's not saving the model artifact natively, but you are producing a model artifact to be able to do that Optuna test. So if I didn't set this to false, it would log all of those to that model registry, and I don't want that behavior. And then the other one, and I'm just now remembering, I forgot to look up what this is. This was actually a AI coding tool recommendation. Serialization format equals skops. I don't know what skops is, to be quite frank. I am very used to saving my scikit-learn models as .pickle files, but like I was getting some sort of warning that was saying that that's not best practice anymore. I should have taken the time to look at what that is. But basically, whenever we actually train our model and then that gets serialized into like a file, typically we would use a pickle file. It's going to get logged as this skops file. Functionally speaking, though, it's the same thing. Okay. And then I want to do a couple other things here. So I don't want to necessarily have too much noise within my log. So I'm actually going to add another environment variable here. I'm going to say os.environ. And this is just a personal preference thing. You don't actually have to do this either. MLflow record vars in model logging equals false. Okay. And then I am actually, with each of our runs, I want to put a timestamp on the end of those runs. So I'm just going to create one simple timestamp here at the top. I'm going to say run time. It's probably not best practice to do it exactly where I'm doing it. I should probably do it further on down, but I'm going to do it here anyway because it doesn't really matter. Run timestamp equals pd.timestamp.now. Time zone, we're just going to do UTC, and then we're going to say .strf time is going to be this thing that I don't want to have to manually type because it's ugly. Okay. In fact, I'm just going to copy and paste that whole line. Okay, so you can see here, this is just kind of like a syntax thing. It's just kind of demonstrating how we would set our specific, how we want the year, form, year, month, day, hour, minute, second kind of thing for the timestamp. So that's that. Okay, so that's doing our imports. We have done a little bit of configuration in terms of getting MLflow set up appropriately. Now let us move into actually doing the hyperparameter tuning. So we're going to work first with the iris data set. So let's go ahead and load up the iris data set appropriately. We're going to say x comma y equals load iris, and then we're going to say return x, y equals true. And then we're going to do a split here. We're going to do xtrain, xval. I guess I'll stick with the typical nomenclature. I'm just not a fan of like them calling it a train test split. I like to call it a train validation split because we're actually using, I mean, most people, when they're using the validation, like when you're doing a split on data that you have the ground truth value for. And when I think of a test data set, I think of a test data set of not having a ground truth value associated to it. So, I don't know, maybe I'm being naive about something, but we'll stick with what scikit-learn expects. So we're going to do train test split, and then we're going to pass in x, y, test size. We're going to do we're going to do a holdout of 20% of that data. Random state equals 42 because why not? And then we're going to stratify on y. All right, so that is simply doing that. So most of the code in this notebook is not like, because we have turned on autologging, most of the code that we're going to be writing today is not even going to necessarily be MLflow related because MLflow is going to be taking care of a good chunk of that for us. So a lot of this code for this next section on hyperparameter tuning, it's kind of robust, but it's robust because of Optuna, not because of MLflow. All right, so the way that Optuna works is basically you build like this skeleton, if you will, of like what you would like your model to be or look like, and then then you can iterate over that that skeleton, if you will, with different parameter options. That way we can again constantly do these different trials to see which hyperparameter combinations are going to be the most ideal. So the very first thing we're going to do is we're going to build a little function that actually builds our model pipeline. So I'm going to call it def build model pipeline, and then we're going to pass in each trial. So this is going to be the Optuna trial. And then we're going to simply just return a pipeline. So this is a scikit-learn pipeline. And this scikit-learn pipeline is going to have two steps to it. The first step is going to be the scaler. Simply put, that's going to be our standard scaler. And I'm not going to cover too much of standard ML concepts today, but the reason that we're doing the scaling is, if you're aware, some of these model algorithms are sensitive to ensuring that your model is essentially I almost use the word equivalated, which is not a word, but it basically puts your data on the same scale. So if you have one feature that's got really big values, like values up into the millions, and you get this other feature that's like 1 through 10, then the standard scaler is going to help to bring those on a level playing field, if that makes any sense. So that's step one. Our step two is going to be the classifier itself. So classifier, and then we are going to do the logistic regression algorithm. Logistic regression. I'm probably going to have to move my face out of the way, so let me go ahead and do that right now. Just be a little bit proactive about that. Okay, and then we are going to pass in a couple different parameters to test with. So we're going to say trial.suggest float, and then we're going to say c 1e to the negative 3, 1e2 log equals true. Don't worry too much about what these numbers mean. It's basically just offering a range of values for Optuna to test here. And then we're going to say solver equals trial.suggest categorical. And then we're going to say solver. And then we're going to test either LBFGS or Saga. Let me get this message out of the way here. Next, we're going to do max iterations. max iter trial dot suggest int max iter 150 to 600. I'm going to test out a range of values in there. Set a random state to 42. Don't necessarily need to do this last one, but why not? Okay, so that is building the model pipeline. Now, we're going to build another function that we can actually, again, pass into Optuna. And this is where you'll like to see, actually start to see MLflow in action here. Yeah, let me go ahead and start writing the code, and then I'll explain things along the way. So let me just say def objective trial. All right. Now, each time we want to build a new version of the model, we need to get it in through this function here. So simply put, we're going to say model equals build model pipeline. We're going to pass in the trial. So that's basically giving us our first model that we're going to be testing out with. Now, let's go ahead and start to see MLflow in action here. We're going to start our first run. So we're going to say with MLflow.start run nested equals true. Now, if you're wondering what this nested equals true here, recall back whenever we were looking at the user interface with this Optuna trial, where we had all of our experiments that you could expand them in the UI through that little plus icon, like it toggled it open. If we didn't have that, what it would do is just put them all in line together. This is just an organization technique, and I like it because it makes things just cleaner. And then we're going to say run name equals function string Optuna trial, and then we're going to say underscore trial dot number. Okay, so that's how we start the run, and then everything else is basically business as usual. It's this is again where auto logging will come into play. So we're just going to fit the model to the data, model.fit xtrain ytrain. And then we're going to get the prediction values using the test data set, the validation data set, model.predict x test. And then we are going to return an F1 score since we're going to base our final success on the F1 score. So return F1 score. And we need to pass in the Y test, the Y pred. It's bugging me that it's not Y preds. Y preds, predictions, average macro. Okay, so that is setting us up for Optuna. Pretty simple in terms of actually working with MLflow, and then we'll actually look at this in action here in a second. Okay, so let's actually go ahead and run the Optuna study here. So the way that we do that here is we're going to say study equal, not study, study equals Optuna dot create study direction equals maximize, and then the study name is going to be iris log reg optimization. Okay, and then we're going to start another run here. So this is actually going to be like the top level of defining so you noted we got the nested structured in here, and you might be wondering, well, where is it nesting under if we've not instantiated anything? I apologize, I should have explained that better. We're actually going to do that here. So we're going to say with MLflow.start run name equals Optuna hyperparameter search, and then we're going to put in our runtime stamp. So this is where I was saying earlier, it probably would have made sense to just generate this on the fly right here, because now everything's going to have the same timestamp of like 6 minutes ago or something like that. Again, doesn't matter for our purposes though, since this is kind of just a simple demo. And then we're going to do study.optimize. We're going to pass in our objective. Number of trials we want to do is 30. And show progress bar, why not? Show progress bar equals true. And then finally, we're going to extract the best params. Best params equals study.best params. And this is all the code that we need for working with MLflow here. At least for hyperparameter tuning, that is. So let's actually go ahead and start up MLflow again. So I'm going to go back into my notebooks, CD notebooks, run MLflow. Do I need to turn on? I might need to turn on my virtual environment again. So by the way, in case you're wondering what that shortcut is, what the shortcut is actually doing is I actually learned that through Git, you can actually use Git to determine the root of the repository. So what it's actually doing is it's going up into the root of the repository and then always activating my virtual environment at source.vim/bin/activate. And since that works for me because that's like with every single Git repo, I always set up my virtual environments the exact same way. So that's why this vimvom command works pretty well for me at least. Anyway, so I'm going to do MLflow server. What is going on here? All right, my terminal's being weird today. All right, repos, cd MLflow tutorial, cd notebooks, them on, MLflow server. Okay, there we go. I'm not sure why my terminal was being a little bit funky today. All right, so let's go back into this user interface then, just to look at things. So we have already created the empty container of the, sorry about that, getting a jump call. All right, anyway. So we've already created the empty container that represents the experiment, but you can see that there's no runs in here. Now, the second that we run this cell right here, we should start to see a bunch of stuff start to get added. So let's go ahead and run this. Do I need to refresh this? Okay, it looks like I needed to refresh it. Now you can see by this run name right here, can I make this bigger for y'all? I don't know if I can or not. Not bad. Workable. But you can see here with this run name that we got hyperparameter search with the timestamp, so that directly correlates to this right here. And then you can see again, like we were talking about, here's the nested piece in action, where we have all of our different runs associated to this nested structure for each of the respective trials here. And then if I wanted to look at any of these trials, I could just click on this one right here. And then again, here's auto logging in action. So we have all of these different metrics that were run here. We have all of our respective parameters, and I did not need to do any of that myself. Now, if I were working with a library that was not supported by MLflow auto logging, then I would have to do, sorry, I'm getting a little bit distracted because I don't know if I have a troll in my YouTube chat, but like somebody keeps asking for an autograph. I don't do autographs. Anyway, so you can see that we got all these different metrics here. I don't think I've ever looked at these other tabs. Oh, this is kind of cool here. It's got, different visuals here representing our different things here. I guess, well, now that I look at it, it's not that helpful, but it's still kind of cool. System metrics, no traces. And then the only things we have as far as artifacts go is just representing the HTML file, HTML representation of the scikit-learn pipeline, and the confusion matrix here. So all very cool. And this was all done with auto logging. So if I did not have, oh, that's where I was going. So if a library is not, or a machine learning framework is not supported by MLflow, then I would have had to do all this manually, which is not a deal breaker per se. It's just not as easy as using auto logging. Or if I want to get way more specific, if I want to give very specific names to some certain parameters for whatever reason, then manual logging is always available to us. And we will demonstrate manual logging here in a little bit. Okay, so that's the Optuna study. So now let's actually go ahead and solidify our final model that we want to train, and we're actually going to use the best parameters from our previous trial for training the final model here. So we're going to start a new run again with MLflow.start run name equals f iris model training. We're going to append our run timestamp, run underscore timestamp. Sounds like my kids just got home from school. I hear people upstairs. All right, so we're going to fix the trial here. So this is kind of a cool feature of Optuna is if you want to continue using like this training pipeline up here, but you know which parameter values you want to do, we can just fix the trial. And so what I'm going to do here is I'm going to say final trial equals optuna.trial.fixed trial and pass in our best params. Then we're going to do our final model equals build model pipeline final trial. Then we're going to fit the training data to the model. Final model dot fit x train y train. And then we're going to get our final predictions equals final model predict x test. And then we're going to, okay, so I'm going to pause here for a second because we're going to introduce a new concept here. Actually, a couple new concepts. So let's harken back to our image here. Now, our image here is not exactly indicative of this, but one thing that MLflow supports for traditional ML is after I have trained my model, I can actually directly host that model for inference directly from the tracking server. And the way this works is that whenever the model gets trained, you may have seen it before, we'll show it again here in a second, we actually are saving a couple of different files that are not just the serialized model artifact itself. And I'll show those here in a second, but basically all those other files represent a virtual environment that is created on the fly using CondaForge. If you're not familiar with what CondaForge is, so if you data scientists out there might know what Anaconda is. So Anaconda is a very popular thing to create data science virtual environments. Now, Anaconda, the company, has since made some changes to their terms and conditions to where, like, if you're a larger enterprise, larger company, then you have to pay licensing fees. And so then the community, I think that the community might have already done this before, but anyway, the community created this thing called CondaForge, which is basically like the pure open source version of Anaconda, or like how you would get dependencies for Anaconda, just in an open source fashion, and then totally bypassing the company Anaconda altogether. So we'll show that in a second here, what all those different files represent, but that is why, but anyway, okay, so that's where I got a little bit lost there. So along with that, we can actually create what is called a model signature. And what the model signature is basically saying, okay, you, MLflow, are going to be serving this model out for inference through the tracking server. How do you know what inputs to expect, what outputs to expect? And that is defined by the model signature here. And simply put, there's actually a really easy way to get the model signature. If you recall, at the top of this notebook, we imported this thing called infer signature. So I'm going to say model signature equals infer signature x test final predictions. Okay, so basically what that is doing is we just gave it our input data and our final predictions, and is basically saying, okay, MLflow, you figure out the model signature for me. Okay, and then we, in addition to the model signature, we can actually provide an input example to kind of harden to MLflow. Okay, you know what the model signature is. Now here's a specific example to go along with that. So I'm going to say input example equals pd.dataframe x test. We're just going to grab the last 5 rows of x test. Columns equals feature idea. And the only reason I'm having to do, this little thing that I'm doing here is when we actually download this data through scikit-learn directly, it's basically just like a NumPy array, so that with no like actual column names directly associated to it. So I'm just creating some fake column names here. Now you'd want to be more careful with a real project here, of course. Shape 1, and yeah, I think that's it. All right, so that's the input example. Now, this next thing here, do I even want to do? Now, you know what? I'm actually going to, so I'll go ahead and show it in my other notebook, but I don't think I'm going to do it in this one. And that is, so this is all the exact same code. When we actually recall when I was mentioning that when we train this model through MLflow and we register it through the model registry in MLflow, it's creating a number of different files that represent our Python libraries and such. You can actually, it's going to infer the different pip requirements that you need. But if you want to accept them more explicitly, you can do it this way. And that was this weird thing that we imported here. You might have recalled this import lib metadata version. That's what this was. So let me scroll back on down here. So if I wanted to be very, very, very specific, instead of having MLflow kind of infer what it thinks is the appropriate dependencies, we can actually hard code them this way. So you can see I'm hard coding all these different versions appropriately. And then we can even go take it a step further and say, okay, if we want and the CondaForge environment to be a very specific way, this is how we would do it. Now, I'm going to be a little bit lazy here, and I'm going to decide not to do that, so I'm going to skip that portion here. But let's continue on with the code anyway here. So we're going to produce some final metrics. And the reason I'm producing them here is because I want to demonstrate how manual logging works. Again, because we have auto logging turned on, this is not particularly necessary, except for the model logging piece, which, as you recall from this piece right here, we intentionally have it turned off from doing the auto logging on purpose because I didn't want all those models from Optuna logged as their own respective models in the model registry. So we will definitely have to account for that down below here. So anyway, accuracy. We're going to produce the accuracy score, y test, and then we're going to do final predictions. Then what are we going to do? Precision macro, precision score, y test, final predictions, average macro. Okay, so that's the precision. Is the next one recall? Yep, the next one is recall. Macro, recall, score, y test, final predictions, average equals macro. And then finally one more, F1 score, F1 macro is going to be F1 score, y test, final predictions, average equals macro, and that is that. And then I basically just produced all these metrics as a simple little Python dictionary here. Now, how do I manually log them to MLflow? That would be as simple as doing MLflow.log metrics, pass in the final metrics. So manual logging is not too bad, and that's why I say, if your ML framework is not supported by MLflows and therefore not supported by auto logging, it is not a deal breaker because doing the manual logging is not really that bad. It's just, I will say I still kind of prefer the auto logging though. All right, so then let's actually log this model out. So let's say model info equals mlflow.sklearn.log model. So we're going to say sk model equals final model. We're going to say the name, we're just going to call it name is, actually I'm going to call iris model. Doesn't necessarily matter. This is just kind of a metadata thing. We need to pass in that signature we were talking about. So we're going to say model signature equals model signature. Input example equals input example. Serialization format equals skops. I don't even know if I have to put that here since I already designated it above, but just to be safe, let's do that. And then we're going to do registered model name. Model. Actually, no, that's fine. Registered model name equals iris model. Now you might be wondering, what is the difference between name and registered model name here? Well, let's say I went back through and I ran this code again at a later point in the future. What MLflow also supports is automatic versioning of things. So basically we have this registered model name. So that's going to be the top level, if you will. And then each time, so we would probably want to change what this specific name here up up here is we might append like that. In fact, let's go ahead and append the timestamp just to demonstrate that. I'm pretty sure this is the correct place to do it. MLflow timestamp, run timestamp. So that way in the future, run timestamp, if we ever ran this code again, it would all get registered and versioned under the singular registered model name, but we could look at it as this little piece here. Is that all I want to do? I believe that is all I want to do. So let's just do a quick review here again. So we're starting the run. We're fixing our parameters, building the model, fitting the model, predicting the model, inferring the signature, getting the input example, producing the metrics, logging the metrics, and logging the model. Okay, and then let's go ahead and run this. Looks like I had a typo. Average, not average. All right, now let's hopefully everything will be okay now. Okay, so we went ahead, and then you can see here that we went ahead and created version 1 of the Iris model. Now let's go ahead and look at that in the model UI here. So I'm gonna go. Let's actually go back, or the MLflow UI. My apologies. Let's go ahead and look at this again. So we have our recent experiments. So you can see here. Let's close that down. Now you can see. Oh, that's kind of cool. I didn't even know it actually registered whenever something failed. I'm kind of curious what it says. So status of failed. Does it say why it failed? Somewhere in here, I don't know if it does or not. Maybe that's something that you have to be more specific about why it failed. Anyway, so let's go back to our run. So now we can actually see that we do have this successful run here. And then if we scroll off to the right here, then we can actually see the model itself over here. Now does this? Okay, that does contain everything I want. So again, we logged all of our stuff using. It looks like it did it twice, actually. So it looks like the auto logging still did apply here. So that's why we see all these things that are training here. But then these bottom 4 down here are things that we actually manually logged ourselves, along with all the different versions and stuff here. Now, let's go and look at the artifacts that I was talking about, where we have the different things that represent like how you would actually serve out the model from the tracking server if you wanted to. So we got a couple different files in here. At the beating heart of MLflow, whenever you want to serve this out, is this thing called ML model. Now, this ML model is not actually a model itself. It's a manifest. And so if you understand what a manifest is in like a shipping context, it's basically like a set of instructions for saying, okay, here's how you actually build this thing, or here's how you actually serve this thing out. So you can see that by default, it's noting that we're going to be using a Conda environment, and it actually creates these different files here that actually help to build the virtual environment represented by the Conda environment. It demonstrates like where our model actually sits, how it's going to be predicted, and then we'll talk a little bit about customization, a little bit of like let's say you wanted to be a little bit more explicit, like with the input-output code, because by default, whenever you actually serve out one of these models from the tracking server, it's just serving the model itself out, and in many cases, what is actually more common is that you actually have some pre and post processing steps, and we'll kind of demonstrate that a little bit later on in the stream. So that is the ML model file. Then we have a couple different other files here. So this is the Conda YAML file. So we talked a little bit about Conda Forge already, and the different things that so it is inferring here. Here are the different pip installs and stuff that you would actually need to actually run this model. I'm going to go ahead and jump on down to PyEnv here, because it's kind of the same idea here, where the Conda YAML and the Python M file here are working in tandem to actually know what specific Python dependencies we need. I guess same with the requirements.txt file. It's also logged in here. Now, this model, the skops, this is actually our trained model here. So this is actually the serialized model. So if we actually didn't want to use MLflow for whatever reason, and we wanted to deploy this model elsewhere, we could simply grab this artifact from this location here and then use it however we would use it on that other platform. And then finally we have our example. So we have our input example here. So that demonstrates our input example. And then same kind of idea here where we have the serving input example. I actually don't know what the difference between these two files is, because by and large they look the same to me. I mean, I do see that there is a little bit of a difference. Excuse me, but I don't know why one would be used over the other. So let's actually demonstrate how to leverage these models, and I want to demonstrate in 2 ways. The first way I want to show is, so we've been talking a lot about that model, the model serving stuff. I want to pause that for a second. I want to show that you can actually use the MLflow client to actually pull the model directly from MLflow and use it directly if you didn't want to use the tracking server. So let's go ahead and pop into our notebook. and demonstrate that here. So what we need to do for that is we're going to instantiate the MLflow tracking server client. So we're going to say MLflow client equals MLflow client. Okay. Now, the very first thing we're going to do is actually, you know what? I'm going to go ahead and rerun this all again, just to show here that now, because we've already the registered model already exists, we're creating a new version of the model. So now we have version 2 of the model. And so if we come back into here, if we go into our model registry or our models here, then we should be able to see, yes, we have 2 different models. So if I come into here and look at version 2, this is where the UI gets a little bit strange, because sometimes like the clicking around things in the UI can be a little bit different than what I'm getting a little bit lost here again. I think maybe this is what I want to click on. So Iris version 2 here, so you can see the respective. Well, this is just showing the run. I don't know. The UI can be a little bit confusing at times, but I assure you, we're good. So let's look. Can I see the artifacts associated in here somehow? Maybe from the source run. No, I get a little bit confused sometimes with this UI, but the reason I want to demonstrate that here is because I'm actually going to search for the latest version first. So latest version equals the maximum of int model dot version model underscore version dot version for model version in MLflow client dot search model versions name equals iris model. Okay, so basically what it's doing there is searching for the latest version. In fact, let me go ahead and just run that and let's look at that. Latest version is 2. Makes sense. Okay, and then we're going to get the model URI. Model URI equals fstring models slash iris model, and then we're going to pass in that latest version. Okay, and then we're going to load up the model again. So we're going to say reloaded model equals MLflow.scikit-learn sklearn. If I can type right, load model URI. And then we're gonna reload. We're gonna just get a simple input here. So we're gonna say reload. I don't know why I called it this. Kind of silly on my part. Reloaded input. We're not reloading anything. I don't know why I called it this. So we're just gonna say we're just gonna grab a couple rows here. Reloaded predictions. I think I just got a little bit slap happy with the reloaded term here. Reloaded model dot predict reloaded input, and then got a couple print statements down here just to kind of demonstrate things, and I'm going to just copy and paste them in because I'm getting lazy. What did I not do here? Oh, reloaded input. There we go. Okay, so you can see that we got the reloaded input, and then we got prediction values back appropriately. So yeah, that demonstrates how if you want to just load in the model without doing the whole tracking server thing, that's how you do it. Now, this next thing that we're going to do is I'm actually just going to copy and paste this code because it's rather complex to type all out, and I'm just going to talk through it. And it's actually not Python code; it's actually just shell code that you would run in the shell terminal. But I'm just going to copy and paste this stuff here. So what we're actually going to be demonstrating in this next section is how you would actually serve the model out from the tracking server and invoke it appropriately. So I'm again, like I said, I'm going to just start the thing up using this bash code here. So let's talk a little bit about the bash code. We're setting a couple of environment variables at the top of where we want these things to run on. So because we've been running everything on port 5000, we're just going to keep incrementing the port number. And then I have code down below that actually makes sure that we can shut everything down appropriately. So this first piece is just simply trying to look for or making sure that the server is healthy whenever we actually start this thing. So this is the actual command that we actually run. We would run in like our terminal if we wanted to start up MLflow as the server with more specifications here. So like by default, this is what we do by default. That probably didn't make any sense. By default, this is like whenever we actually ran like MLflow server over here, I believe that these are all the same parameters anyway, so it's not particularly necessary to do what we're doing here. And then we're actually going to use a little bit of Python code to actually do a health check here. So let's go ahead and run this just to demonstrate that this thing works. MLflow server is running healthily at port 5001. Okay, great. Now let's go ahead and grab the code for the next cell here. All right. It's a little bit long. All right. I'm trying to highlight it all on one block on this bottom screen here, and I'm struggling, as you cannot see. Oh my gosh. You know what? I got a better idea than that. Why don't I just grab it from here? Okay, so we already did that. So let's grab this code right here. Okay. I'm going to grab this code right here. So again, we were just exporting some simple environment variables and noting some log files and such. And this is where this is how we would actually get our run ID. So we're running a little bit of Python code to get the runs. It looks like so transparently, I did use AI to help me write some of this code. So it looks like there's a couple different ways you can actually search runs here. So this is actually how this little piece here is actually getting I just realized that this should be local demo. Local demo. This should also be local. I did have this formerly named before, which is why I need to go and update that code. But anyway, so this is basically just searching for the runs to ensure that we are getting the latest version. And then we are going to serve it out. So this command here is actually the command that we would run on our terminal to actually serve out that specific model as a real-time endpoint. So that's what that is doing. We're again doing another ping here for a health check, and then when we scroll on down here, this is actually the payload that we are using to invoke the model. So we're producing the payload using a little bit of Python, and then we're using a simple curl command to actually get the invocation here. So let's go ahead and run this cell. So the model started healthy, and then we see that when we print out results, we get the exact same results that we did from this cell above here. Great. So that demonstrates how you can actually use MLflow to actually serve out the model as a real-time endpoint, call it, and then just as a cleanup measure, I'm going to grab this code here. This is just cleanup code. This is just making sure that I'm not leaving anything hanging on any of those port 5000 or 5002s here. So I'm not going to necessarily explain what this code is doing. I'm just going to run it, and it's going to, I mean, by default, it should be that like after this cell had completed that everything was shut down anyway. And this is just like an extra check just to make sure, because I've gotten burned before where I accidentally left something running on a like a port 5000 and tried running another thing on a port 5000, and it's like, whoa, no, something's already running on port 5000 and blah blah blah. And so that's why I got this cleanup code here. So we don't need to worry about that so much. Now, so that is that. Now I do want to cover one final thing, and that final thing is, so like we were saying, when we actually train this model and we serve it out behind the MLflow tracking server, it is just hosting the model itself. No pre-processing code, no post-processing code. So what I want to demonstrate, and the way I'm going to demonstrate it here, is we can actually get more customization for how to actually interact with the tracking server if we wanted that additional customization. And so recall when at the top of Notebook we had loaded in the wine data set. The way I'm going to demonstrate this is by actually sliding in two models to serve behind one endpoint here. So what we actually need to do first, though, is we actually need to train the model, that wine training model. How are we doing on time? All right, we're already at over an hour, so I'm just going to copy and paste this code because this code is almost the exact same as what we did before. We're not going to do any hyperparameter tuning this time, but I'll go ahead and talk through it. So we're going to load in xwine, ywine from the scikit-learn helper function there. We're going to do the split here. Again, same stuff that we've seen before. Then we're going to instantiate a simple random forest classifier with some very simple parameters that are not hyperparameter tuned with this wine model object. Then we're going to start the run here. And this run here, again, we're seeing this should be nothing new to you. This is the same thing that we saw above whenever we were working with the iris data set. We fit the training data to the model. We get the predictions. We infer the signature based off of the X-test and the predictions. We produce a simple little example. We produce some validation metrics. We log those metrics manually, and then we log the model here. Again, this is all the exact same stuff. So let's go ahead and run this cell, and let's go look at it in the MLflow UI. So if I go back to our model registry, now we have this new wine model here. So if I wanted to look at version 1, I, again, do not know where to click on things in this UI. It could be a little bit confusing sometimes. I think the easiest way is actually to go to the experiments, look at the local run demo, and then you can actually see it here off on the right where we got this thing that says run, I'm sorry, I'm moving too fast. I'm clicking faster than I'm talking. So we got this wine model training run here, but then you can see off on the right that we actually have the model associated here, and I didn't give it any particular name. If you can see back in the code here, I just called it model. But let's go ahead and run it again just to show that, like, if I run it again, we're going to get version 2 of the model. So then if do I need to do a refresh? I might need to do a little bit of a refresh here. So yeah, now we have a new run here for our new train of that model for version 2. And then when I click on this here, then you can see that, yes, this is down here, this is the version 2 of the model. And then we can see all the different stuff that we were looking at before. Again, auto logging has captured some of this stuff for us already. And then we also had our various values that we logged here. Again, I just want to highlight one more time, we're not trying to produce a perfect model here. And the reason I note that is it should be fishy to you that all these values are 1, because they're fishy to me for sure. But again, that doesn't matter for this, for what we're doing here. We're just kind of demonstrating how MLflow works. We got all the different parameters that were logged here, including ones that we didn't even touch. These are just all the other default values associated with the random forest classifier. And then, of course, we have all the different files that we were looking at before that helps to serve out the model. Now, this is where things get a little bit more complex, because we were talking about, well, what if we want to serve 2 models behind the same endpoint? So let's go back into our code here. So the way that this works, it looks like I forgot to move some imports to the top of my notebook. I like to keep my imports all at the top, but looks like I missed some. So let's go ahead and add them here. So import JSON from typing import any. So the way that MLflow works is it uses under the hood this thing called PyFunk. And I need to learn a little bit more about PyFunk, because I think PyFunk is not particularly exclusive to MLflow. I have seen it in my work with Databricks. It looks like it's used a little bit more widely on Databricks as well. But at least in the context of MLflow, what PyFunk can do is we can actually define very specifically, okay, here's the logic that I want to build, and then actually register this logical thing that we're building as its own model, if you will. And then when we serve that out, then we actually have the customized thing that we want to get inferences from. So basically a multi-model endpoint. So the way that we do that is we're gonna go class multi-model router. We're gonna and this is gonna inherit from mlflow.pyfunk.python model. And then we need to create a couple different things in here. So of course, sorry, didn't mean to say of course. So we're gonna do def. Well, I did mean to say of course. I thought there was an init thing in here, as most classes offer, but apparently there's not. So we're gonna do load context. We're gonna do self context, and then we're gonna say self.models equals iris mlflow.sklearn.load model context.artifacts iris model. Okay, and then we are also going to load in the wine model here, not wind. Wine mlflow.sklearn load model context.artifacts wine model. Okay, now we need to create another function here. So this is where the magic happens here. So we're going to create our own custom predict function here. So predict. So by default, it's just invoking the model, and that's it. But we're going to have a few extra goodies. So we're going to say self. Context is going to be the mlflow.pyfunk Python model context, model input. Is going to be a pandas data frame, pd.dataframe, and params is going to be a dictionary of either strings or any. None equals none. Okay, and then what are we expecting to get back? Well, we are expecting to get back a pandas data frame. Okay. Now let's go ahead and write the logic for our function here. Why is the indentation not? I put all these on separate lines in my notebook. I think I'm going to put them on a single line just to kind of help myself make sense here. Because I'm kind of confused why maybe it's because I put this extra comma over here. Okay. There we go. Now it's doing proper indentation. Okay, so we're going to say required columns equals. All right, so we want to see that whenever, so this is basically saying, okay, when somebody calls our custom endpoint here, we want to make sure that they have two required columns, model name and feature station. Now, what this is actually doing is whenever the user invokes the model, it's noting by the model name which model it wants to invoke. It's not as if we could set it up this way. It's not as if you run the wine model and then you run the iris model. It's that per the user's input with this model name here, that's going to designate which model that we actually want to invoke here. So we're going to say missing equals required columns dot difference model input dot columns. Okay, and then if it's missing, we're going to raise a value error f missing required columns sorted missing. Okay, that's just making sure. So this is basically just input validation here is what those three lines were. All right, and then we're going to create a list to hold our predictions, because we can pass in multiple records at a single time, and then we can just predictions, and then we can return them all at once. So we're going to say for row in model input.iter rows. So this is basically saying, okay, let's iterate over any data that we got in. If we have multiple records, that's what this is kind of doing. So we're going to say selected model equals str row model name dot strip dot lower. Okay, then if selected model, this is another little piece of just input validation in self dot models. So basically saying, all right, we're grabbing the selected model, the model that you want, and if it's not there, we're going to raise another value error. Raise value error f unsupported model name. Uh-oh. Didn't mean to do that. Selected model valid options are iris or wine. Okay. Then let's go ahead and get the raw features from the input. Raw features equals row features JSON. Then we're going to check to make sure that this is a string value type. If is instance raw features, if they're strings, then we're going to load them up. Feature values equals JSON.loads raw features. And if they're not, then we're just going to say feature values are the raw feature values equals raw features. It's getting hot in my office. It was really cold earlier, and I turned on my space heater for like an hour, and now it's like sweltering in here. Okay. All right. So features equals np.as array feature values, d type equals float. And then we're going to reach, not float, float dot reshape 1, -1. And let's go ahead and get our prediction routed. Prediction equals self.models selected model dot predict features, and then we're going to get the value from that first index thing there. Then we're going to do predictions dot append model name selected model, and then we're going to do prediction is going to be a float value of our routed prediction. And then finally, we're going to break out of that for loop, and we're going to return pd.dataframe predictions. Okay. Yeah, so that's the router itself. Uh-oh, looks like I got a syntax error. Yep, I forgot a comma. More syntax errors. This is how you know AI didn't write the code. It's because they don't make silly mistakes like I do. All right, so now we actually need to, so we're going to take this class thing here, and we're actually going to register it as if it's its own model. So let's go ahead and demonstrate that here. So first thing we need to grab the respective model artifacts representing those trained models. So we're going to say iris artifact path equals MLflow.artifacts.download artifacts artifact URI equals models iris model / latest. And then we need to do the same thing for wine, and I'm going to be a little bit lazy and just copy and paste this and just change a couple things because it's basically the same thing minus name difference there. Okay. Then we need to actually create a couple. We're going to create an input and an output example. Now we do I need to do both? Hold on, I'm just looking here. Yeah, we're actually going to create both here because we can't actually infer the signature here per se because it doesn't have any examples to work from because this is our own custom thing. So we're going to say router input example equals pd.dataframe, and we're going to say it's going to be a list dictionary model name iris features json.dumps x test 0.toList. Okay, thank goodness for syntax highlighting, or else I'd be so confused by all those parentheses there. And then we're going to do another one for the wine model name wine features json.dumps. Oh, that would be why. X wine test 0.toList. Okay. I almost went to go take a drink, but then I realized I don't have a drink today. Bummer. All right, so that's the input example. Let's go ahead and create the output example. Router output example equals pd.dataframe. And then the outputs, what are they going to look like? So we're going to have a model name of iris, and we're going to have a prediction. And then just for dummy's sake, we're going to just call it 0.0. Same idea here. I'm just going to copy and paste this down. Change that to wine. And then now we can actually infer the signature by providing these specific examples. We're going to say router signature equals infer signature. And then we're going to pass in our router input example, router output example. And then finally, we are going to register this thing. So we're going to say with MLflow dot start run name equals f pyfunc multi model router run timestamp and then we're going to say router model info equals MLflow.pyfunc.log model. Name is going to be model, because I don't really care what this is named here. Python model. This is where we actually pass in that class that we instantiated above. So multi model router. I lost my place. Oh, there we go. Artifacts. Artifacts equals iris model, or iris artifact path. Oh my gosh, come on. There we go. Wine model, wine artifact path. And then we're going to do a signature. It's going to be that router signature. And then finally, we need the registered model name. I'm going to call it multi-model router. And then I'm going to do a little print statement here at the end just to kind of signify that we actually did everything. So print f router model registered version, and then we're going to say router model info dot registered model version. Okay, so there we go. This will take a second or so, and there we go. So we officially created version 1 of the multi-model router. Now let's go ahead and run it again, just so that we can create a secondary version on top of that, and then we'll go look it back in the UI here. So let's go back to local demo. So now we can see that we have our PyFunc models that are kind of showing up in here. So then if we click on this over here, now this is our models. So you can see now that we have a nested directory of artifacts here because we got a couple of different things. Well, I guess it's just manifesting as one because it's going to be pulling, if you notice from the model artifacts here, that it should be pulling from wherever those model artifacts are. Maybe it's this register model meta. I don't know. Looks like we got a couple extra files in here that, oh, there we go. The python model.pickle file. That's what I was looking for. Okay, so that is it up in MLflow. So let's finally demonstrate how we can actually invoke it in the same way that we were from the tracking server. So we're going to be running some bash commands again. Again, I'm going to be, since we're already running up on an hour and a half, I'm just going to go ahead and reuse my code that I have already created here in my completed notebook. So I'm going to take all this code. I'm going to copy and paste in here, and I'll explain it, of course. And then this is the second one. Code. Okay, and then there's my third one. All right, so we have 3 cells here. We'll talk about these 3 cells. Actually, I'll just briefly mention this third cell. This third cell. Okay, sorry, I got confused by cell and shell there for a second. It's just doing that cleanup activity that we were doing before. But anyway, so this first one, what we're doing is we're starting up the tracking server. We're determining what, or we're just checking for the health of the server. And then finally, with this secondary cell here, this is where all the magic happens. Now, when we set all these different things, so like when we want to get the versions of the multimodal router, or multi-model router, then we set the router URL, and then we run this MLflow command, MLflow model serve. We pass in that router URI, we host it out on this port, we designate our ports, we start it up, we check the health, we produce a little bit of a payload here, and then we pass that payload in with a curl command, and then finally this third cell will actually do that cleanup that we're talking about. So let's go ahead and run this first one, and then we should see a health check is healthy, all good on port 5003. I'm just doing it on different ports just to like specifically call out, yes, we're using different ports. That way it doesn't seem like we are doing any sort of other funny business with anything that we've done before. And then finally, if we run this, this is the magic cell here. So, oh, it looks like I messed something up. What did I mess up? Okay, invalid parameter value, failed to predict model name. It's probably because I changed something in here. All right, so I'm gonna ditch this notebook and let's go ahead and just run my like actual, because I probably just named something strangely in here, but I know this code works for sure. So let's go ahead and run my my completed notebook, if you will, here. So and then you'll be able to see all these values show up appropriately. So this is running everything right now, and you can see that everything runs rather quickly because we're using some simple model artifacts and such. Oh, looks like I screwed something up here. Okay, so I've got some sort of mess up in here. I'm not really sure what I messed up per se. But yeah, like basically at the end of the day, if you want to get more customized with actually like the code that actually invokes the model, you basically just use PyFunc there. Okay, so let's wrap things up here really quick to kind of talk through what we kind of covered today here. So again, this is the MLflow UI. We have everything that rolls up to experiments. Experiments are not necessarily what you think they are. It makes sense in the context of hyperparameter tuning. And again, and it'll become even more clear why the experiment nomenclature is now what, I don't want to say irrelevant or outdated per se, because like you can like the term experiment in general is rather ambiguous, but in MLflow, it is easiest to think of it as a collection of runs. And so then again, so if we look within our experiment, we got all of our respective runs. We use auto logging and different things to help us capture metadata and such associated to each of the runs. And then after we trained our models, we can look at them in the model registry. And then if we wanted to serve them directly from MLflow, we can do that through that MLflow model serve command that we were demonstrating before. And I think that's all I want to cover today. That is basically MLflow for traditional ML at a high level. Now, of course, there are other things that we did not cover today, such as securing MLflow. So obviously security is of utmost importance. And so it does offer features to place like an OAuth layer in front of it, things like that. But that's MLflow for traditional ML. Now in the next stream, or maybe two streams, again, I haven't decided if it's going to be one or two streams yet. I want to cover the other half of MLflow. So this is the newer half of MLflow, and that is all associated GenAI stuff. So I hope that at least with this first stream, we got a sense of how MLflow works. That way, when we go to the new stuff with GenAI, we have an understanding of, oh yeah, that's why experiment is called an experiment. That kind of idea. So I'm going to go ahead and wrap up here today. Hope you all have a great weekend. I will see you in the next one.